All right, continuing along with areas of triangles. Check this out. I want to get the area of this triangle to the nearest thousandth, so 3 decimal places. In a previous video, we proved any triangle is 1/2 base height. But remember, the base and height have to be perpendicular to each other. So we could think about, are these sides perpendicular? Is that a right angle? By checking, is 5 squared plus 7 squared equal to 10 squared? Pythagorean check, and it turns out it is not. So this doesn't look possible at first because we don't know the height of the triangle. But so that's an H. I'm trying to write sideways, so that's an H. The whole bottom side is 10. So hopefully you agree, if we knew the height, we could get the area. It would be 1/2 times base 10 times the height. So the work becomes figuring out the height. I don't know how long this is. I'm going to call it X. I don't know how long it is from here to here, but we can call it that whole 10 minus that X. So if you want to challenge yourself, and if you pause the video in a second and write out a system of equations with 2 variables. Pythagorean theorem for this triangle, just write out the first line of the Pythagorean relationship. And then next to that, write out a Pythagorean relationship, an equation for these 3 sides. And see if you can solve each equation for h squared. So if you want to try that, hit the pause button. And here we go. So on this triangle, h squared plus x squared equals 5 squared, or h squared plus x squared equals 25. To solve for h squared, I just subtracted the x squared from both sides, so I got this. For this right triangle, h squared plus the other leg squared equals the hypotenuse squared, and that of course is 49. And when you expand out 10 minus x squared, 10 minus x times itself, it becomes 100 minus 10x plus x squared. Or 100 minus 20x plus x squared. So you can pause the screen and check my algebra there. But if from this line, so this is my equal sign, I subtracted 100 from both sides, I added 20x to both sides, I subtracted x squared from both sides, and that got me down here. So h squared is this. Over here we said h squared is this. Well, that means that this and this must be equal. They're both equal to h squared. So we can set this equal to this. Down here I did that. And the only nice part of this whole process is there's a minus x squared on each side. So by adding x squared to each side, those terms cancel out. So we just have this little linear equation. I added the 51 to both sides. I divided by 20. So x is 3.8. That's the good news. Bad news is we didn't want x, we wanted h. So I went back up to either of my original equations. I took the first one, which was h squared plus x squared equals 5 squared. And down here I substituted my x value. So h squared plus, and now I know x is 3.8. 3.8 squared equals, and then the 5 squared is 25. So if you go through that algebra, you'll quickly get the height to be exactly the square root of 10.56. And about 7 minutes ago we said this would be an easy problem if we just knew the height. Well, now it's an easy problem. Half base height. There's the picture again. Remember, the base was 10, and we just figured out the height is the square root of 10.56. So I fill in my base, I fill in my height. Half times 10 is 5. So there's my answer. It says nearest thousands, so 3 decimals, 16.248. So it turns out it was possible to do, even though we didn't know the height. I wrote down some more digits here I want to refer back to later that my calculator was showing, but this is the answer to the nearest thousands. Wouldn't it be nice if there was a formula that lets you find the area of a triangle when you only know the side lengths and you don't know the height. Here is a formula, not in your book. Very little known formula, to be honest. Most people do not know about this. This is not in your book. I'm going to show this to you. Heron's formula, discovered a little over 2,000 years ago by Heron. He also went by the name Hero, not a joke. He was able to prove if you know the sides of a triangle, you can get the area without knowing the height. And in his formula, the sides of the triangle are ABC, and the letter S stands for semi-perimeter, half of the perimeter. And he proved that the area of any triangle, doesn't have to be a right triangle or equilateral, any triangle is going to be this formula. The square root of the semi-perimeter times the semi minus one side times the semi minus another times the semi minus a third side. I'm going to try to remember to post a link to a proof of this formula if you're interested in it. There is a proof that doesn't require trigonometry, but the algebra in it is insane. But if anyone's curious, I'll try to remember to link that. So let's try this. Here is the same triangle, 5, 7, 10. Heron says the area has to be the square root of semi-perimeter. Well, the perimeter of the triangle, if we add up the side lengths, is 22. So I guess the semi-perimeter, half of that is 11. So that would be the square root of 11 times 11 minus 10, which is 1, times 11 minus 7, which is 4, times 11 minus 5, which is 6. The order of these doesn't matter, but it's the semi-perimeter minus one side, semi minus a second side, semi minus a third side. So that gets us the square root of 6 times 4 is 24, times 11, 264. And on the calculator, the square root of 264, get a look at that. And compare that to the previous answer, 5 root 10.56, that is the exact same number. 16.24807681, and those will keep going forever and keep matching. This is the exact area of a triangle, Heron's formula. So, let's quickly try a couple that we already would know the answer to. This triangle I would normally not get with Heron's formula. Normally we would just say, well, it's a right triangle, missing side has to be 4. Normally we would just say area is 1/2 base height, and that's going to come out to be 6. Just for practice, Heron's formula would say the square root of semi-perimeter, so 5 plus 4 plus 3 is 12, half of that is 6, times the semi-perimeter minus one side, semi-perimeter minus another side, semi minus the last side. So that's going to be 6 times 3 times 2, and 6 minus 5, 1. 1 times 2 times 3 times 6 is 36. Square root of 36 is 6. So last one for this video is a triangle we've now done twice. We did this in our first video with 1/2 base height. We also did it with that special formula that's only for equilateral triangles. Side squared root 3 over 4. And the answer we got was 25 root 3. Let's try Heron's formula. So, perimeter is 30, semi-perimeter is 15. So square root of semi-perimeter times the semi-perimeter minus one side of 10, so 15 minus 10 is 5, times that semi-perimeter minus another side of 10, that's another 5, and the same with the semi-perimeter minus the third side of 10. So that comes out to be the square root of 1875. And if you were to break this down, Keep dividing by perfect square factors of 25. Or if you recognize it, you'll see that this actually can be simplified as root 625. That's a perfect square times root 3. And we do in fact get the same answer, 25 root 3. So this kind of triangle, I would always use this formula if I know a side length on equilaterals. If it's a right triangle, or any triangle, if I know base and height, I would use 1/2 base height. But if it's a triangle and we don't know the height and it's not equilateral, I would use Heron's formula rather than going through all that work. Hope you got something out of that. I'll be back with the next video soon.